students, welcome back to the JEE Last Mile Preparation Series 20. Today we will take up the last two questions of this series, 39 and 40. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEEchemistry.in, and we have been bringing you two questions every day to help students get that extra edge for their JEE chemistry exam preparations, and exams are around the corner. Let's get started. We continue with inorganic chemistry, and today we will solve two questions from a very important topic, coordination compounds. So here is question number 39. Okay, let's first read the question, understand the question, and then we will try to get the right answer. Low spin complex of D6 cation in an octahedral field has the following energy. So four options have been listed here. Four options have been listed here. One amongst the four options will correspond to the energy of the low spin complex of D6 cation in an octahedral field. Okay, so let's solve this question in detail. First, let's try to understand what is meant by a low spin complex. Okay, you know that a complex ion is formed between a central transition metal ion, right? Central transition metal ion and surrounded by ligands. Correct? The type of bond between the transition metal ion and the ligands are dative bonds or coordinate bonds. Now, when we talk about an octahedral field, it implies that there are six dative bonds. There are six dative bonds surrounding the transition metal ion. The ligands could be monodentate. If the ligands are monodentate, then there are six monodentate ligands around the transition metal ion. If there are bidentate ligands, you know there are three bidentate ligands around the transition metal ion. We count the number of dative bonds, and we know that the coordination number, therefore, is equal to 6. The ligands may be monodentate, bidentate, hexadentate. We count the number of dative bonds only around the transition metal ion, arrive at the coordination number 6, and if the coordination number is 6, then the field is octahedral and the geometry of the complex is also octahedral. All right. Now, so we've understood what an octahedral field is. Coming back to a low spin complex. Now, there are two types apart from the monodentate, apart from the denticity, apart from classifying ligands based on the charges, neutral, positive, negative, or based on the denticity, monodentate, bidentate, hexadentate, polydentate, etc. Ligands are also classified based on the strength created, the strong field ligands and the weak field ligands. Now, this classification is based on the extent to which the d orbitals are split. Okay, so we will soon discuss that. You're already aware of that. So in strong field ligands, the difference in energy between the split d orbitals in an octahedral field. In other words, delta O corresponds to the crystal field splitting energy is found to be greater than the pairing energy. In other words, they rather get paired than undergoing transition. In a weak field ligand, right? When the ligands are weak field ligands, in such a scenario, the difference in energy between the split d orbitals or the crystal field splitting energy of an octahedral complex will be less than the pairing energy. So pairing of electrons require more energy. The difference is less. So electrons rather undergo transition. d transition occurs. d transition occurs, resulting in the formation of or resulting in the occurrence of or presence of many unpaired electrons. So when there are unpaired electrons, the magnetic behavior is normally paramagnetic. Okay, and these normally produce high spin complexes. High spin complexes. So paramagnetic implies the presence of many unpaired electrons. So you're adding up the spins of all the unpaired electrons, resulting in high spin complexes. On the other hand, if the ligand is a strong field ligand, the crystal field splitting energy is greater than the pairing energy. So the electrons get paired. Okay, so pairing of electrons occur where? In lower energy. The lower energy d orbitals are the 3t2g orbitals, right? So pairing of electrons occurs. When pairing of electrons occurs, the magnetic behavior is mostly diamagnetic or weak paramagnetic. There might be just one unpaired electron that makes it a weak paramagnetic, as a result of which they produce low spin complexes. Okay, low spin complexes because there are very few or hardly any unpaired electrons. So that is the background information regarding low spin complexes and high spin complexes. Okay, so now let's try to find out how the electrons in a D6 cation, the transition metal cation, are distributed. Okay, so we have here the degenerate 5d orbitals, right? The 5d orbitals are the degenerate orbitals. Degenerate d orbitals. Okay? All right? Now, and there are 6 electrons. 1, 2, 3, 4, 5, 6. Now, this is a D6 transition metal ion. When ligands approach this particular transition metal ion, these degenerate orbitals get excited, right? And when the complex ion is formed, when the ligands form dative bonds with the transition metal ion, that is when the excited degenerate d orbitals undergo splitting. Okay, so here we have, let me write down this, let me draw this line here, which we call as the barycenter. So on splitting, what happens is, splits into EG orbitals, which is dx square minus y square and dz square. And the others are, the other 3 orbitals are the 3 T2G orbitals. So 2 EG orbitals and 3 T2G orbitals. The 3 T2G orbitals are dxy, dxz, and dyz, the orbitals. Okay, the d orbitals, 3 d orbitals are those, and here dx square minus y square and dz square. All right, so that's about the splitting of the d orbitals. Now we're talking about an octahedral field, and therefore the total energy difference between these two d orbitals, these two levels of d orbitals, is given by delta O, which is the crystal field splitting energy of an octahedral complex, delta O. Out of which, so this is the barycenter. Barycenter is the average, is where the d or the degenerate d orbitals are present, hypothetically. Okay, so this part corresponds to lower energy, so minus 2 by 5 delta O, and this part is plus above the barycenter, so higher energy than the degenerate d orbitals, plus 3 by 5 delta O. So 3 by 5 plus 2 by 5 would be delta O, 5 by 5, so delta O. This can also be written as 3 by 5 delta O can also be written as 0.6 delta O plus 0.6, and this is minus 0.4 delta O. Okay, so you've learned all this. Now let's find out what is the formula to determine the crystal field splitting energy, a general formula. So that is given by if number of electrons in the x corresponds to electrons here, okay, at the T2G orbitals. So I'll write down those details. So minus 2 by 5 delta OX plus 3 by 5 delta O into Y plus ZP. Okay, so that is the formula of crystal field splitting energy, where X corresponds to the number of electrons in T2G orbitals, Y corresponds to the number of electrons in the EG orbitals, and Z corresponds to the number of paired electrons. Okay, the number of paired electrons, and P stands for the pairing energy. We already discussed what the pairing energy was, right? So these are the various the details of this formula. Now let's substitute for a D6 cation. For a D6 cation, the CFSE equal to minus 2 by 5 delta O into, there are how many electrons in the T2G orbital? Let's distribute. Now, because it's a low spin complex and delta O is greater than the pairing energy, right? So delta O, the difference in energy is greater than the pairing energy, transition becomes difficult. Transition from the lower energy d orbitals to higher energy d orbitals becomes very difficult. You need the large amount of energy has to be absorbed. So rather pairing occurs. Okay. So when pairing occurs, all the 6 electrons will be accommodated in the lower energy d orbitals. So there are 6 electrons in the T2G orbital and 0 electrons in the EG orbitals. So let's substitute those values. So 6 plus 3 by 5 delta O into 0. 0 electrons in the EG orbital plus. There are 3 pairs of electrons. 1, 2, 3. 3 pairs of electrons. 3p. Okay. So what does this become? Minus 12 by 5 delta O. This is 0 plus 3p. So this will be the crystal field splitting energy of a D6 cation, low spin complex D6 cation. Okay, so let's go back to the options. So option B would be the correct answer. Minus 12 by 5 delta O plus 3p is the energy for a low spin complex of D6 cation in an octahedral field. All these terminologies are important. Okay, so that is about question number 39. Let's now move on to question number 40. Another important property shown by complex ions, the color. Most complex ions are colored, so some are colorless. So that is clearly understood from this question. Out of TiF62 minus, COF63 minus, Cu2Cl2 and NiCl42 minus, what are the colored species? So 4 options have been listed here. Okay, and 2 pairs of species have been listed in these 4 options. Which amongst the 4 options has got both the species as colored species is what we have to identify. The atomic numbers of all the transition metals involved here have also been given. Okay, so our first step is to find out what is the criterion for a transition metal complex ion to exhibit color. We have already discussed the splitting of d orbitals in our previous question, right? So we have delta O, which is the crystal field splitting energy, right? So the frequency corresponding to delta O is absorbed. Okay, absorbed from where? Because we are talking about color, is absorbed from visible light or visible part of the electromagnetic spectrum, from visible light. So the appropriate frequency corresponding to delta O is absorbed from the visible light, and the complementary color. You have learned all this. You may recall a color wheel. A complementary color will be transmitted. The complementary color is transmitted. Never use the word emitted because this is an absorption spectrum, not an emission spectrum. So complementary color is transmitted. Okay. Now, the frequency absorbed is used for what? The frequency absorbed is used for undergoing transition, for the electrons to undergo transition from T to G to EG. Okay, so the frequency absorbed is used for DD transition. What do we mean by DD transition? From lower level T2G orbitals to higher energy level EG orbitals. Okay, so this transition will for the electrons to undergo this kind of a transition, what should be absorbed? An appropriate frequency corresponding to delta O. Delta O is the difference in energy between the two split D subshells, right? Will have to be absorbed from the visible light. Only then the complementary color will be transmitted and the color will be shown by that particular complex ion. Okay, so that is the background information regarding how complex ions exhibit color. Now we have to identify what is the other criterion required for a transition metal complex ion to exhibit color. Okay, now focus on these two configurations of the transition metal ion. So transition metal ion, okay, metal ion of D0 and D10 configurations. Okay, in other words, we are focusing on D0 transition metal ion and D10 cation, D0 cation and D10 cation. When we talk about D0 configuration, there are no D electrons. When there are no D electrons, obviously no DD transition occurs. There are no electrons to undergo transition. Splitting will happen. Whenever ligands approach a transition metal ion, splitting will happen. After the splitting happens, for the electrons to undergo transition, there should be electrons in the d orbitals. So if there is a D0 configuration, the T2G orbitals are empty. So there are no D electrons for DD transition. And if there's no DD transition possible, or if there are no D electrons, no frequency is absorbed from the visible light, and as a result of which such complex ions will be colorless or white. Okay, same is the case with the D10 configuration. D10 configuration implies that T2G is 6, okay, and EG is 4, which means the 3 T2G orbitals and the 2 EG orbitals are fully filled. So there are no available electrons are there. There are 10 D electrons. But what is missing? No available D orbital for transition. To accommodate the electrons, there are no available D orbitals. So no DD transition occurs, right? As a result of which, the D10 metal cations will also produce colorless compounds or white compounds. Okay, so that is the criterion. So if any transition metal ion has a D0 or a D10 configuration, they will not show, no DD transition occurs, and therefore they will not exhibit color. They will be colorless, right? So what is the important criterion here? For color to be exhibited, the D orbitals should be partially or incompletely filled. So this is an important requirement for a transition metal complex ion to exhibit color. Partially or incompletely filled D orbitals. In other words, the configurations of the cation can be anywhere from D1 to D9. Okay, so that is the background information. So we have completely discussed the background information for a transition metal complex ion to exhibit color. Now let's focus on the question. The first complex ion given in the question is TiF62-. TiF62-. let's find out the oxidation state of the titanium ion. Okay, so X plus, each fluoride ion is -1, 6 of those, so -6 is equal to -2, the overall charge on the complex ion, and therefore X is equal to +4. So Ti has a +4 plus charge, or the coordinations, the oxidation state of titanium ion is +4. Now let's write down the configuration of titanium 4 plus. The condensed configuration, argon, which corresponds to 18 electrons, right? So atomic number of titanium is 22. So 22 minus 4 is 18. So this is the configuration of titanium 4 plus, which implies that 3D has got 0 electrons. 0 electrons corresponds to no color or colorless, right? So immediately we can rule out those options which involve the titanium 4 plus ion. So we can rule out options B and C. All right. Now let's focus on the cobalt hexafluoride ion. Number 2, COF6 3-. Cobalt is X, -6 is equal to -3, X is equal to +3, right? So the oxidation state of cobalt is +3. So cobalt 3 plus ion, cobalt has an atomic number or nuclear charge of 27. So that is equal to argon, 27 minus 3 is 24, 18 electrons, and then we have 6 electrons in the 3D subshell, and hence DD transition will occur and therefore will exhibit color. So colored complex. All right. So we can immediately identify the option that, well, we have this option here, COF6 3-. Okay. So now we have to look into the other two complex ions and finally arrive at a conclusion. Now let's move on to Cu2Cl2. In Cu2Cl2, number 3, Cu2Cl2, the oxidation state of copper would be +1, right? So this is +2x -2 is equal to 0. So that would be X is equal to +1. So copper is in the +1 oxidation state. So copper 1 plus, 29 is the atomic number. Argon, 18 electrons taken care of. We need 28 electrons, right? So copper would have been 4s1, 3d10. So now we have 3d10, right? So 18 plus 10 is 28. We need 28 electrons to be accounted for. D10 configuration corresponds to what? A colorless complex ion. No DD transition occurs. Now let's move on to the last, and then we will arrive at the final conclusion. The last one is NiCl4 2-, right? Yeah, NiCl4 2- complex ion. So X -4 is equal to -2, or X is equal to +2. So nickel is in the +2 oxidation state. Nickel has a configuration of, so atomic number 28. So 28 minus 2, 26. Argon, 18. And then we have 3D8, right? So this is D8, and therefore it will exhibit color, colored complex. So I hope the theory behind formation of colored complexes is very clear to you. So now let's arrive. We have arrived at the final answer. The final answer is also wrong because Cu2Cl2 is colorless. So the correct answer to this question would be option D. Both cobalt hexafluoride ion and nickel tetrachloride ion are colored. Okay, so option D is the correct answer. At the end of the JEE Chemistry exam preparation series, I would like to wish all students good luck for the forthcoming JEE exam. May you all score high marks and secure admissions to the courses and colleges of your choice. If you found today's video useful, please like the video and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Thank you.